For the first time since the Apollo 17 mission in 1972, humans will cross the magnetopause and enter deep space. For the last 50 years, human spaceflight has been confined to low Earth orbit. The International Space Station operates about 250 miles above the surface, well within the safety of Earth's magnetic field. The Moon sits nearly 1,000 times farther away. Navigating this 240,000-mile gap falls to the Artemis II crew, led by Commander Reid Wiseman. Once their spacecraft crosses the magnetopause, the planetary magnetic shield disappears. The crew is exposed to the raw interplanetary medium, directly facing highly ionizing solar radiation and galactic cosmic rays. Pushing a crewed capsule into this environment requires calculating an orbital trajectory that solves multiple conflicting physical threats simultaneously. Mission planners have to balance 4 strictly opposing parameters: limited spacecraft propulsion, the mandatory validation of new life support systems, radiation avoidance, and an absolute guarantee of abort safety. During the Apollo program, NASA solved the propulsion problem with the Saturn V's massive S-4B upper stage. It carried enough fuel to push the command module directly from low Earth orbit out to the Moon in a single continuous burn. Artemis II operates on a different architecture. The Space Launch System rockets the Orion capsule off the pad, but the primary upper stage is discarded before the spacecraft leaves Earth's gravitational neighborhood. This creates a severe engineering tension. Orion's remaining onboard engine lacks the raw power to execute a direct translunar injection from a standard low Earth orbit. To overcome this thrust deficit, Artemis II abandons the direct launch profile. The mission uses a multi-day high Earth orbit staging sequence instead. This mathematical model maps the Earth. After launch, the interim upper stage places the Orion capsule into a highly elliptical initial orbit, with a low point of 115 miles and a high point of 1,800 miles. At the high point, the upper stage performs an apogee raise burn. This maneuver stretches the trajectory into a high Earth orbit, or HEO, pushing the spacecraft's farthest point to approximately 46,000 miles from the surface. Coasting along the slow outer edge of this ellipse takes 24 hours. Because the Artemis II capsule has never flown with humans on board, this long temporal window gives the crew time to validate their life support systems while they are still trapped within Earth's gravity well. After confirming the systems are operational, the crew conducts a proximity operations demonstration. Orion physically detaches and backs away from the upper stage. From this moment forward, the spacecraft relies exclusively on the European Service Module engine for propulsion. The crew has now severed physical ties to their primary launch power. They must rely on Orion's onboard capabilities to build the momentum needed to reach the Moon. The European Service Module utilizes a repurposed orbital maneuvering system engine from the Space Shuttle era. It produces exactly 6,700 pounds of thrust. That thrust profile is physically incapable of efficiently pushing a 58,000-pound spacecraft from a circular low Earth orbit all the way to the Moon. This visualization tracks the spacecraft at the perigee node, the lowest altitude of the high Earth orbit. As the craft falls back toward Earth, it builds immense kinetic energy. The velocity vector arrow maximizes. Because the spacecraft is already traveling at high speed through this energetic ellipse, the physical demand on the engine drops. The service module only needs to add approximately 1,274 feet per second of velocity to the existing momentum. By firing the engine exactly at this perigee node, the combined velocity vectors compound, snapping the spacecraft into a new trajectory that breaks away from the closed orbit. The maneuver works kinetically, but it introduces a strict environmental hazard. Dipping back down to a 115-mile perigee forces the spacecraft straight through the densest regions of the Van Allen radiation belts. Solving the propulsion deficit using orbital mechanics places the crew directly in the path of severe ionizing radiation. The mission must now rely on physics to mitigate the dose. Looking at this equatorial cross-section of Earth, we can see the Van Allen belts, 2 toroidal regions filled with high-energy protons and electrons. Charged particles from the solar wind and cosmic rays are trapped here by the Lorentz force, causing them to spiral continuously along Earth's magnetic field lines. To minimize exposure, Orion follows a highly inclined orbital path relative to the magnetic equator. The trajectory slices through the belts at a steep angle, bypassing the densest equatorial core entirely. Geometry provides one layer of defense. Kinetics provides the second. Because the translunar injection burn occurs precisely at perigee, the spacecraft is moving at its absolute maximum velocity as it enters the bolts. This high-speed transit compresses the time spent inside the most hazardous flux zones to less than 1 hour. By moving fast and entering at an angle, the crew's cumulative radiation dose is kept to roughly 5% of an astronaut's career limit. Artemis II bypasses the need for mass-prohibitive lead shielding by weaponizing velocity and orbital geometry as a physical shield. When the service module engine cuts off, the spacecraft must hit a strict kinetic boundary, exactly 24,500 miles per hour. This map of the Earth-Moon system shows what happens if the spacecraft exceeds that limit. At 25,000 miles per hour, the spacecraft possesses too much kinetic energy. It achieves hyperbolic escape, overshooting the Moon and flying out into deep space. At exactly 24,500 miles per hour, the spacecraft remains governed by three-body gravitational dynamics. The trajectory approaches the Moon's sphere of influence without breaking free of the system. Earth's gravity acts as a continuous anchor. It constantly decelerates the spacecraft, maintaining exactly enough influence to pull it back. As the spacecraft reaches the Moon, lunar gravity does not capture it. Instead, the gravity well bends the velocity vector around the far side. This creates a precise figure-8 path, aligning the velocity vector for a direct return to Earth's atmosphere. This specific path provides operational redundancy. Even if the service module suffers a catastrophic failure, gravity guarantees a safe splashdown in the Pacific Ocean. The 24,500 mile per hour limit is the mission's ultimate failsafe. It converts raw orbital mechanics into an automatic abort mode. 4 days into the flight, the spacecraft reaches the magnetopause, the physical boundary of deep space. This visualization models the strict magneto-hydrodynamic equation that defines the boundary. The magnetopause exists at the exact point where the dynamic pressure of the solar wind equals the magnetic pressure of Earth's field. As Orion pierces through this fluctuating boundary layer, it leaves Earth's protective envelope behind. Outside the magnetopause, the crew loses all planetary protection. They are entirely exposed to sudden solar particle events like coronal mass ejections and solar flares. Protecting the crew now shifts from orbital mechanics to material science, relying heavily on hydrogen-rich mass. The atomic physics are highly specific. A hydrogen nucleus has nearly the exact same mass as a high-energy solar proton. When the two collide, this equal mass ratio allows for maximum kinetic energy transfer, effectively absorbing the radiation. If solar monitors detect a coronal mass ejection, the astronauts will physically dismantle their storage bays. They will rearrange water supplies, food rations, and plastics against the hull's weakest points to construct a dense storm shelter. For secondary defense, the astronauts carry astrorad vests, which provide targeted shielding to protect organ-rich areas and bone marrow from penetrating doses. The Artemis II egress requires solving a thrust deficit, navigating the radiation belts, locking into a free return trajectory, and engineering physical radiation shields. Returning humans to deep space relies on a precise balance of orbital phasing, magnetic physics, and material science.